Hey, what's up, everyone? We are going to look at graphing a quadratic again and just review the process of how to graph a quadratic equation. The first thing that you'll see in this practice problem is that we have a quadratic that is in standard form that we talked about, right? So this is an, ax squared plus bx plus c form. And so since it's already in that form, our strategy is going to be to find the middle of the parabola, to find the axis of symmetry, and then plug in some key points to find solutions to that equation that we can graph on the equation. So our first step is going to be to find the axis of symmetry, which is really part of finding the vertex or the middle of our graph. So that's always going to be the first x value that we utilize or plug into our function. So that x value is going to be negative b divided by 2a, and that never changes. It's if we have standard form, then we take those parameters and do the opposite of b over 2a to find the middle. So in this particular case, we're going to have positive 6. Okay, so the opposite of b, in this case, b is negative 6. So the opposite is positive 6 divided by 2 times a, which is 3. And so we get 6 over 6, which is 1. So again, for like an XY, chart here, we're just sort of showing the different types of solutions that we could have on here. Of course, there's an infinite number of solutions, and the x values, the domain is all real numbers. So we could plug in any number into the function. We're being strategic here and plugging in the best x value to start with, the most important one, because that is the middle. So we're going to start by plugging in 1, which is the axis of symmetry. So we can fill that. I'm just going to fill that in right here. That x equals 1 is our axis of symmetry. Also on our graph, we might as well make a little dotted line, which is really just a guideline to say, hey, look, this is not the graph, but this is going to be the center of our graph. And our graph will have this line symmetry or be mirrored about that x equals 1 line. Okay, so as in any sort of XY chart, we have an x value. We want to find the y value, so we're going to plug in 1 into the function. So let's go ahead and do that. We're going to plug in f of 1, or plug in 1 into the function. And again, I like to sort of map out what our rule is by putting parentheses around our inputs. So if it's 3x squared minus 6x plus 3, I'm saying 3 parentheses squared minus 6 parentheses plus 3. Now, of course, we could generate these solutions and whatnot with a calculator, and we could speed up this process, but definitely want to encourage you to be able to do these things by hand, and certainly know how to evaluate expressions and not kind of forget any of the true basics, PEMDAS and all that kind of stuff. So if I plug in 1, okay, go through here and evaluate. So this would be 3, 1 squared is 1, minus 6 plus 3. So we really have 3, oops, fix that. 3 minus 6 plus 3, which in this case is going to give us 0. Oops. All right, so that is our vertex. So our vertex is 1, 0, and we can start by putting that on the graph. Now we also know that our graph is going to open upwards because our a value, remember, is positive. So we just kind of know that it's going to open up. And then we're just going to fill in some more solutions so we can kind of sketch out a decent looking graph. So another point to pick, we talked about before, but we could plug in 0 is always kind of an easy one typically. If we plug in 0, that immediately gives us the y-intercept, right? It's also an easy one to evaluate because 0, multiplies 0 to those two terms. If I plug in 0, I'm going to get 3, right? So f of 0 is 3. So I'm going to go ahead and plot 0, 3 really quickly. And then we can sort of leverage the symmetry here. So just by looking at the graph, we know that the point over here, if we mirror that over that line that we already made, the axis of symmetry, we know that 2 also goes to 3. Right? We could double check that, but we can be fairly certain that 2 goes to 3 just by looking at the symmetry. And then we just want to plug in one more point typically on these graphs just to make to have 5 total points. Right, so we're going to pick an x value that is around the neighborhood that we've already been working in. So 2 is the highest x value that I've used. I'll use 3. So I'm going to plug in 3. So then I'm going to do the same thing and plug in 3 into my function and evaluate that. So if I take 3, plug it in, on the right-hand side, I'm going to use my order of operations to get 3 times 9 minus 18 plus 3. So this is 27 minus 18 plus 3. So that's going to give me 12 total. Okay, so 27 minus 18, 9 plus 3, 12. So 3 goes to 12. And that, on our scale of graph, pretty much goes off the graph probably because I think we got a 10 by 10 here. Now we should also know, so let's double check that real quick. All right, 3 goes to 12, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, so it goes off the graph. And so I'm going to still do it and approximate 12 to be up there. We also know that -1 has to go to 12 just by looking at the symmetry of the situation, and so that's right here. So we can just sketch this out. We have enough points here. We're going to just do our best, and of course this kind of increases really fast because the a value is that's kind of a bad sketch. But filling in the rest of these key characteristics, the domain is all real numbers, so we would say -infinity to +infinity if we're using interval notation. And then the range would be the y value. So what y values are possible here in this in this function, and that would be anything from 0 to infinity. So y is greater than or equal to 0. Interval notation would look like that. The roots, remember the roots basically is another word for what are the x-intercepts of this graph in this context. So the roots here, the only x-intercept that we have happens to be the vertex. So there happens to just be one root, or I should say x-intercept in this problem, and I'm just going to say the root here is at 0. X equals 1, right? X equals 1 is where we have a x-intercept, and that's where the y value is equal to 0. Min and max, right? We do have a minimum value here because we have a low point on the graph, and the minimum value is, well, it happens at 1, but the actual minimum value is describing what the height is, what the y value is. So the minimum value is 0 because we're only talking about the smallest range value, not the smallest, like domain value. And that is it. That's the general process for graphing a quadratic by hand. In standard form, that is, we're going to take that standard form, we're going to find the vertex, our critical point first, and we're going to generate more points on the graph by just plugging in more points into the function. and then the key characteristics are right there as well.